Okay, so the other type of trig we might want to differentiate is inverse trig. That's like sine to the -1 or cos to the -1. However, we're going to introduce a little handy shortcut before we do. And that handy shortcut is this, that if you have dy dx, that's the same as 1 over dx dy. It's essentially a use of the chain rule. You could write it out as dx dy times dy dx equals 1, which is essentially true. And the opposite also applies. Dx dy can be found by doing 1 over dy dx. I want to show how this works in a non-trig context before we apply it. So here's a standard exam question. We've got x equals y plus 7 over y squared. We want the equation of the tangent when y equals 4. Now if we want to find an equation of a tangent, we need to find dy dx when y equals 4, because that's going to be our gradient. But we can't find dy dx because this is an x equals equation and it can't be easily rearranged. So instead, we have to find dx dy. Now, how could we do this? Well, we may as well use the quotient rule. We're sort of getting used to it at this point. So we would say u is equal to y plus 7 and v is equal to y squared. And it's actually du dy we'll be finding this time, which is 1. And dv dy is equal to 2y. Quotient rule, so we want to do v du. So this is our dx dy is equal to v du. So that's y squared minus u dv. So minus 2y brackets y plus 7 all over v squared. So that'll go to y to the power of 4. It looks messy, but yeah, it should be fine. We could simplify the top, but there's actually not really any need here. Because our dy dx is just 1 over this, so we'll just flip it upside down. We'll say this is y to the 4 over y squared minus 2y, y plus 7. Now, you might be thinking, oh, that's annoying, it still isn't in terms of x, and that's true, but we can get around that because it tells us a y value that we can sub in. So we are going to substitute in that y equals 4 to this, and that's going to give us that our gradient is, what, 4 to the power of 4 over 4 squared minus 2 times 4 y plus 7, so times 11, which I'm just going to type in. It gives us an excellent gradient of minus 32 over 9 is what I got. Okay, so we have our gradient, which is this minus 32 over 9. We have a y coordinate, which is 4, so we probably need to find an x coordinate as well, and we're going to find that by subbing in y equals 4 to this. So that would tell us that x is equal to 11 over 16. Fair enough. So we've got two coordinates, we've got our gradient, so we can go ahead and we can find the equation of the line. Y minus y1 is equal to m x minus x1. Okay, I am not going to expand that out or simplify it down. Just wanted to make you aware of this little dx dy, dy dx shortcut you can get from one to the other by doing its reciprocal. Okay, so we're going to apply that rule to some inverse trig. Now, with inverse trig, you'll sometimes see the phrase arc sine x, and calculator-wise, you should think about that as sine to the minus 1 of x. Those two mean the same thing, but in exams, they're going to say arc sine. We want to show that if y is arc sine x, then dy by dx is 1 over the square root of 1 minus x squared. Now here's how we're going to do that. We're going to apply sine to both sides. So that's going to give us sine y on the left, and on the right we're going to have sine of sine to minus 1 of x. And what sine and sine minus 1 do is they cancel each other out. That's the whole point. It's the inverse of trig. So we can just say, or you could just go straight to this line, that sine y is x. And why is that useful? Well, it means we can differentiate this using dx dy to cos y, and then we can flip it upside down to get dy dx is 1 over cos y. That's great, but it still doesn't look like what we want it to. There's still y's in it and there needs to be x's, so we need to do something else. What we're going to do is we're going to take this from here and we're going to try and write down what maybe cos y could be in terms of x. So remember that cos squared of, well, we're on y, plus sine squared of y is equal to 1. That's an identity. So we could easily also say that cos squared is equal to 1 minus sine squared. That's one of the ways we can rearrange that. Now in this case, as we're told that x is equal to sine y, we can sub that straight in and we can say in this formula, cos squared y is equal to 1 minus x squared. So there we go. We take that and that, put them together, and we can say that dy dx is equal to, so if that was cos squared y, we want the square root of that obviously, 1 over the square root of 1 minus x squared. Alright, and that general principle of applying sine or cos to both sides of an equation to get rid of an arcsine or an arctan, that's what we're going to use on the next couple slides. So I would recommend at this point you pause, you have a go, because it's the idea of the proof that's important, not just watching me do it. Your exam question is generally going to say, you know, show that this is the case, and it will tell you what you're working towards. Here we've got our arc cos, which is cos to the minus 1, so we're going to apply cos to both sides, and that will get you to cos y equals x. We're then going to do dx dy again, which is minus sine y. We're then going to flip that upside down, if it'll let me. Dy dx is equal to minus 1 over sine y. And then we're going to use the same little trick we used before. So we know that it's true that cos squared y plus sine squared y is equal to 1. So it's also true that we just want sine this time. So sine squared y is 1 minus cos squared y. So in this equation, it's true that sine squared y is 1 minus x squared. Again, using our little definition over here. We want sine y, and I think I didn't write this on the last slide, so I will do this time. So we are square rooting both sides, which is why we're sticking a square root together. Put these both together, and this will give us that dy dx is equal to minus 1 over the square root of 1 minus x squared. Okay, one more to go. Can you guess what it is? That's right, it's arctan. Give yourself a pat on the back. So we're going to apply tan both sides in this case. And again, I'd like you to see if you can take it from there. See if you can get to the thing we're trying to show. Assuming you've done that now. Differentiate both sides. Again, find dx dy, which is sec squared y. Remember, that's one of the things we introduced in the previous PowerPoint. We're then going to flip it upside down and make this 1 over sec squared y for dy dx. We're going to have to use a different identity this time because we're not connecting together cos and sine, we're connecting together tan and sec. And the identity we're going to use is this, that tan squared plus 1 is equal to sec squared, one of those reciprocal trig identities. What can we do with that? Well, tan y is x, we just took that, so we can swap out the tan squared y for an x squared. So x squared plus 1 is equal to sec squared y, and would you know it, that's exactly what we want. We can combine these two things together and say dy dx is equal to 1 over, let's change the order, 1 plus x squared. Proof. So again, these formulas are given to you in the book. You are not required to learn to memorize these, but you could be required to prove them. But as they are given in the formula book, they can also build them into like chain rule and that sort of questions. So I'm just going to look at 2 chain rule questions to finish off. So our first one is we're going to look at y equals arc cos of x cubed, and we're not going to start by applying cos to both sides because we already know now what arc cos differentiates to. We're going to say that y is equal to arc cos of u, and u is equal to x cubed. This is definitely a chain rule because the x cubed is nested within the arc cos. Then we can say dy by du is equal to minus apparently 1 over 1 minus u squared in a square root, and du by dx is just 3x squared. So we'll multiply those two things together to get our dy by dx, and that will give us minus 3x squared all over the square root of 1 minus, we want u squared, so that's going to go to x to the power of 6. Fair enough. This second one, a little bit trickier. We've got arctan of 1 minus x over 1 plus x. So we know that arctan has this as its differential, but that's for arctan of x. So we need to use a chain rule here. We need to say y is arctan of u, and we need to say u is 1 minus x over 1 plus x, and we want to differentiate them both. So we'll go dy du is equal to 1 over 1 plus u squared, What about du dx? Well, we're actually going to have to approach that as a quotient rule with 1 minus x on the top and 1 plus x on the base. So this is like, I guess, our u. Maybe don't want to use that. Maybe say w of v. I'm going to say that w is equal to 1 minus x, and the differential of that is just minus 1. And v is equal to 1 plus x, and the differential of that is 1. And using the quotient rule, we want v dw, take away w dv. So that's going to be minus lots of 1 plus x. Again, we're only finding du by dx here. Minus w dv, so that's going to be take away 1 lot of 1 minus x, all over v squared, so all over 1 plus x squared. What can we do with that? Well, we could expand these brackets out. So let's times this one by minus 1 minus x, and times this one by minus 1, so minus 1 plus x, all over 1 plus x squared. And that would simplify, well, the x's would cancel out. So we'll just end up with minus 1, we'll end up with minus 2 over 1 plus x all squared. So we can now go back to the actual differentiation, still in progress, and we can sub in minus 2 over 1 plus x all squared. Okay. Then we can use the chain rule, which is to multiply dy bu by du dx. So we're going to times those two things together, and that'll give us that dy dx is equal to minus 2 over 1 plus x squared times 1 over 1 plus u squared. So plus 1 plus, and then u is 1 minus x over 1 plus x squared. Now, I'm sure there's things we can do with that to make it nicer, but you know what? I'm not going to do them. I'm just going to answer the question that's in front of me, which is to differentiate arctan of 1 minus x over 1 plus x. So yeah, hope that makes sense.